Okay, let me go over that problem that you just turned in. I promise you, on the first midterm, there will be a problem like that. Before every midterm, I give you at the D2L site 2 old exams and their solutions. And you're going to notice that each of those sample exams will have a major component that is a walk in the woods sort of a problem. In this problem, you went north 16 kilometers and then you went east 10 kilometers. Now this is an old exam problem. Everyone did that correctly. And then things went wrong. They all got the 16 kilometers north. They all got the 10 kilometers east. And the trouble was this third part of the journey, 20 kilometers at 37 degrees south of west. Now, mistakes were made. One common mistake was knowing how to place that 37 degrees. The key word here is of. And that tells you what the reference direction is. We're of west. So if I have a standard north, east, south, west, west is my reference direction. And from west, I can either go north or I can go south of west. Well, we're told to go south of west. Well, how much? A little bit or a lot? Well, 37 degrees south of west. So this angle here is the 37 degrees. And the common mistake that was made on the exam was to make that the 37 degrees, which gives you the wrong answer. Now, the other big mistake that I saw over and over again as I was grading it was they drew their picture like that. Now, folks, if that's 10 kilometers, that's not 20 kilometers. But they could not bring themselves to cross that line, okay? It was like they were werewolves and they could smell it. No, we've been there before. We're not crossing that path. They're lost. They're in the woods. It's dark. They went the wrong way, okay? Now, what you're looking for is that resultant vector right there. Now, another mistake that was made is that once they saw these 2 triangles, they tried to make those the triangles that they worked with. Those are never the right triangles that you want to work with. What we're looking for is the x part and the y part of our answer. That's the triangle we want to work with. The x part and the y part are always going to be perpendicular to each other. You're always guaranteed that that's a right triangle. You don't know whether this is a right triangle or not. This one is, by coincidence. But people were trying to use law of sines, law of cosines, law of Tuesday. It was crazy. Here's how you do it. Well, first of all, you have to draw the displacement vector from the first starting place to the last ending place. Now, in order to add up the components, I have to break that green vector up into its x part and its y part. Okay? Now, on the solution here, I went south and then west. But I could have done this. I could have, if that's my vector, I could have gone west and then south. That's my 37 degrees. Now remember, 37 and 53 are those special angles we look for. Those indicate that we've got a 3, 4, 5 triangle. That the sides are in a ratio of 3 to 4 to 5. Now, since this is 20 kilometers, I know that it must be 5 times 4 kilometers. And so this must be 4 kilometers. Times 4 is 16. And this is 3 times 4 kilometers, or 12 kilometers. Okay? Now, when I label parts of a vector diagram, I'm only putting the magnitude, the size, how far did you walk, always a positive quantity. But when I put them into, so notice I've got a positive 12 and a positive 16 kilometers. But when I put them in my table, I've got to do it relative to some coordinate system. And you can see that initially I'm going in the positive y direction, then I go in the positive x direction, but sometimes people miss these minus signs. In order to get from here to there, I got to go west, that's negative x, I got to go south, that's negative y. Both of those have to be negative. When I add up my x part and my y part, I get negative 6 for the x, positive 4 for the y, and that tells me what my resultant vector looks like. It says go to the west 6 kilometers, and then go north 4 kilometers. That's pretty straightforward. And here's the thing. If you try to do it the hard way by using the law of sines, you might get the right answer in this one. But if I had made a problem with 23 different heights, the law of sines isn't going to do anything for you. This column is just always going to work. Whether you've got 3 heights or 23 heights, it's always going to work. And now I just put the parts back together, and I find the magnitude of the resultant vector by using Pythagorean theorem. I find the angle, that angle there, using the inverse tangent, and I find 34 degrees, and it's north of west. The key being of west, I can go north or south. It's north 34 degrees. See if your neighbor is going to be able to work a problem like that on the midterm. Do a buddy check. Now, that slide right there is taken right from the homework solution that's going to be posted at 5 o'clock today at the D2L site. Every day that we have lecture, you can go at 5 o'clock and download the solutions and check your answers. You can't just assume that you got everything right. You should check your answers. Okay? Now, the tutorial homework for this week's tutorial is due next Tuesday. You'll turn it in on the second floor in the atrium. There's a big open area with large windows. Below those windows there are boxes with your TA's name on it. Just throw your homework in there. The Learning Center opened this week. This afternoon I'll post the schedule and who's in that Learning Center at what time of the week. And again, the homework solutions, as I said, are at D2L. Okay, let's talk about kinematics. We introduced this idea of instantaneous velocity last day, where the delta t in our operational definition had to be small. Small enough that we didn't have time to speed up or slow down. Small enough that the motion during that interval of time looked uniform. was a straight line position versus time graph. Now, when we have a graph like that, we recognize that it's not uniform. Now, we have a wonderful lab activity where you actually move your body in front of motion detectors, and it helps you figure out how to draw these graphs. It's really a good experience. Unfortunately, we only have enough setups for the engineers, so we lose. So what we're going to do is we're going to do a cheap version of that activity. We're going to let me be the object that moves, and we're going to move on a coordinate system that goes positive towards the open door, negative the other way, and that will be the origin of our number line. So, if I want to make that graph, that velocity, position versus time graph, where should I start? At the origin. Which way should I go? Towards the open door? Towards the open door. Should I start fast or slow? Slow. I start with 0 velocity, and then I slowly take off, and then get faster and faster as I go. Fat man running. Okay? Now, what we learned last day was that if we wanted a velocity versus time graph, what we needed to do was collect data points. We go in at different times. This will be noon. This will be 1 second afternoon, 2 seconds afternoon, 3 seconds afternoon. So at noon, I would draw a tangent line. I would take any 2 points on that tangent line and compute the slope. I can eyeball that. It's got a slope of 0. Okay? And so I would put a data point there. At time noon, I have a velocity of 0. I then do that for 1 second afternoon. I find the slope of that tangent to be 2 meters per second every second. Okay? And I put that there. I'm sorry, I misspoke. I found it to be 2 meters per second. Full stop. Period. I do that at 2 seconds, and the slope of that line is 4 meters per second. I keep doing that and collecting data points. At some point I get bored and I just connect the dots. Now that graph is a straight line. Whenever I have a straight line graph, I want to interpret the slope. What interpretation can you give this slope? What does that slope tell you about this object?
Acceleration.
It's the acceleration, that's the name. But what interpretation can you give this? It turns out that the slope is 2. What does 2 tell you about the motion of this object? Yes, sir?
It's accelerating at a uniform rate.
Okay, it's got a constant acceleration. And what does 2 tell me about that motion?
It's accelerating at 2 meters per second every second.
Okay, and where would I see that? If this was a car that was doing that, where would I look to see that happen?
Speedometer.
On the speedometer, yeah. What would happen is I'd look down at the speedometer. If I happen to have one of those fancy cars that read in meters per second instead of miles per hour, it would be increasing by 2 meters per second every second that ticks by. Okay? Now if I take the slope, I take the rise over the run, and I would get 2 meters per second per second. Now I would like you, please, to pronounce it this way. 2 meters per second for each second, indicating that this second is part of the change in velocity that happens on your speedometer, and it happens in a unit of time, 1 second. Okay? Good, thank you very much. So this is my operational definition of acceleration. You used it during tutorial this week. And remember, it's important that we always take 2 data points to calculate our change. Always 2. You remember the analogy with the weather. If you want to know what the weather is, stick your head out the window. If you want to know how it's changing, you got to stick your head out, pull it in, wait 5 minutes, stick it out a second time. Okay. Now, in this class, we are going to concentrate on problems where the acceleration is constant. By that I mean that the velocity versus time graph is typically going to be a straight line. Now, that's not always going to be true, but primarily. And that's because there's enough richness, there's enough mess with these types of problems. We don't need to go looking for more mess. Now, you'll notice for constant acceleration, the distance traveled in equal intervals of time is not the same. However, the change that happens on the speedometer would be the same. In every 4-second interval of time, we change our velocity by 20 centimeters per second there. Okay, simple problem. A car is moving 50 miles per hour east. 10 seconds later, it is moving at 70 miles per hour east. Find the car's acceleration, magnitude, and direction with your neighbor. Would you please solve that? Okay, let's do it together now. The final velocity is 70 miles per hour east. The initial velocity is 50 miles per hour east. That change happens in a time of 10 seconds. That's going to be a change of 20 miles per hour east in a time of 10 seconds, and that's going to give me a final answer of 2 miles per hour for each second east. Okay, magnitude. The magnitude is this number. That's always going to be a positive quantity, and the direction is east. Okay, let's try another one. A bear is running at 4 meters per second north. The acceleration of the bear is 3 meters per second squared. Now, meter per second squared is a legitimate unit for acceleration. It's what's used in most textbooks. But sometimes trying to visualize a square second is tough. So I'm going to try, whenever possible, to write that as 3 meters per second for each second. The question is, what's the bear's velocity 2 seconds later? So really quick with your neighbor. What's the bear's velocity 2 seconds later? Okay, what's the answer? Shout it out. 10. Okay. The acceleration is the same direction as the initial velocity. That means every second that ticks by, we're adding a change vector in the same direction as the velocity vector. That's going to make my velocity vector longer and longer. This bear is speeding up. If this bear had a speedometer in his belly, it would start out with a reading of 4 meters per second. Every second that ticked by, that speedometer would move up by 3 meters per second. So it would start at 4. After 1 second, it would be at 7. After 2 seconds, it would be at 10. It's that simple. Now, this should bring back fond memories. This is just what you did in tutorial, except I'm giving you numbers here. And I'm setting up a coordinate system where up the ramp is positive and down the ramp is negative. Now, based on those numbers that I gave you, What is the acceleration of that ball with your neighbor? What is the acceleration of that ball? Would anyone like to ask me a question?
What's the time right now?
What's the rate of photo taking for the strobe?
What's the what?
The rate of photo taking for the strobe, or the time between?
Oh, the time between strobes, it turns out, is 2 seconds. Ah, that changes everything. Yeah, okay. Now what's the acceleration? Okay. If we use that operational definition, it's just the final velocity minus the initial velocity. Okay? Well, the final velocity is 6, positive 6, minus positive 9. That's going to give me a negative 3 meters per second change over a 2-second interval of time. That gives me an acceleration of minus 1.5 meters per second for each second. What does that minus sign mean? Does it? We'll see.
Well,
Okay.
it depends on the direction.
In one-dimensional problems, we use the minus sign to indicate direction. We choose one direction to be positive, one to be negative. I wish it weren't so. I wish that people who came before me in this job had chosen otherwise. I wish they would have chosen green to be up the ramp and teal to be down the ramp or something like that. They chose plus and minus. And it turns out that it confuses beginning students. But we're gonna live with it. Now, we know that acceleration is down the ramp because this is what we did in tutorial. We took the initial velocity and we put it tail to tail, heel to heel, with the final velocity. And we asked ourselves, what change would I have to add to that long vector up the ramp to get a short vector up the ramp? Well, the addition, the plus sign is right there. This long vector plus this vector in the opposite direction gives me the final vector. Okay? Now, if that change in velocity vector is down the ramp, the acceleration vector has to be, no other possibility, must be down the ramp. Tell your neighbor why that is so, and in your explanation, use the words flux capacitor. Now, do it. Flux capacitor. What I just claimed was that this vector would always, every stinking time, be in the same direction as that vector. And the reasoning is as follows. Unless you have a flux capacitor and a DeLorean, delta T cannot be negative. You cannot go backwards in time. Mickey marches forward. If you take a vector and you divide it by a positive number, you get another vector in the same direction. In other words, if this is the vector C, then the vector C over 2 is going to be half as long, but in the same direction. The vector C over minus 2 is going to be half as long in the opposite direction. This can't happen to this equation without a flux capacitor and a DeLorean. If you don't know what I'm talking about, you have missed some fun movies. Okay? Go back to the future. Okay. Now, key point. Acceleration is a measure of the change in the velocity vector that occurs in one unit, typically a second, of time. Now, these pictures here come from Cutnell and Johnson. This is the textbook that we would be using if we weren't using our textbook. This textbook costs $260. I put this up here just to show you what you're missing. Those are crummy pictures. Okay, this airplane has an acceleration of 9 kilometers per hour for each second. What that means is that if we start at noon with the plane at rest, every second that ticks by, the speedometer goes up by 9 meters or kilometers per hour. I show this picture because it's just wrong. That acceleration should not be labeled with a negative number. If you've got an arrow to the left, that tells you it's to the left. And you should always just put the magnitude. So I'm showing you that $260 doesn't buy you much. Okay? But if we just ignore that mistake, this drag car starts with a velocity of 28 meters per second, about 60 miles an hour. And each second that goes by, I have to add -5. So I go 28, add -5, 23, add -5, 18, add -5, 13. That's the basic idea. Now, what's wrong with this statement? Acceleration tells how fast the object is moving per second. Why is that not only wrong, but sick and wrong? Brave soul?
Because it's not how fast it's moving per second, but it's ever changing.
Okay, so the whole idea of a change is what's missing there. The change in velocity is missing. What about this one here? Acceleration tells how much the velocity increases.
Acceleration can also tell us how it increases.
It could also be decreasing. What else is missing here?
As a unit of time.
In a unit of time. In a unit of time. So it's got 2 problems there. Okay, suppose I were to tell you that you're in a car, and that car has an acceleration of -7 meters per second every second. Is that car speeding up or slowing down? It depends on your coordinate system. It depends on your coordinate system. Okay, let's look at an example. Suppose that we have a long straight freeway, and that freeway goes between 2 cities. And we're going to call the positive x direction the direction towards Billings. And we're going to call the negative x direction the direction towards Butte. And that's not a social statement. I'm just setting up a coordinate system. Now, if at noon you have a velocity that is 28 meters per second, and I've got this acceleration that is, it's negative, but in this coordinate system I would represent it with an arrow to the left, and I would put the magnitude. At exactly noon plus 1 second, how fast are you going? Yeah, 21 meters per second. If, however, you were originally going towards Butte at 28 meters per second, and this were your acceleration, this would be, in an equation, this would be negative 28 meters per second, the negative sign meaning toward Butte, with an acceleration of negative 7 meters per second. At noon plus 1 second, you would be going 35 meters per second. Still in the negative direction. Okay? Now, many times, textbooks use the word decelerate to mean, well, sometimes they use it to mean slowing down, and sometimes they use it to mean negative acceleration. Well, we've just found that those 2 different uses of the word decelerate are inconsistent with each other. So in this class, we're never ever going to use the word decelerate. One of the words we'll just agree not to use. When we want to say that something is slowing down, we will say it's slowing down. That works. Okay? Now, let's look at this example here. If we use the operational definition of acceleration as the ball is speeding up down the ramp, we take final, which is -9, minus the initial, which is -6. -9 minus -6 is -3. You divide that by the 2 seconds and you get negative 1.5 meter per second every second. Same as before. That minus sign means down the ramp. And in this case, it means speeding up. Okay? Now, the key idea is that there are two vectors that are important to motion: velocity and acceleration. When those two vectors are in the same direction, either both positive or both negative, you're speeding up. When one of them is positive and one is negative, and it doesn't matter which is which, you are slowing down. Okay? Now let's just really quick, just for the heck of it, let's look at this problem SP1. You were asked in part of this problem, at t equals 2 seconds, right there, is car B speeding up or slowing down? Now, folks, some people misinterpret these problems as being problems with curves on the road. This is a long, straight road. This car is either going in one direction or the reverse direction. This car does not need a steering wheel. Okay? And these numbers on the side just indicate mile markers along the road. If this is Bozeman, this might be Butte, that might be Billings. These are mile markers along the road. Now, when I think about speeding up or slowing down, that's a process that takes time. So if I look at what happens during this period of time around t equals 2 seconds, the slope of that tangent line gives me the velocity. Is that a positive slope or a negative slope? Negative. It's a negative slope. And it's kind of steep. As time goes on, that slope gets less and less steep. And indeed goes to 0 right there. Is that car speeding up or slowing down? Slowing down. Now the fact that the slope is negative means that it's going in the negative direction towards Butte. If the velocity is negative and it's slowing down, what flavor of acceleration does that car have at 2 seconds? Positive or negative? Positive. It's got to be opposite the velocity. Now, here's how I know it's positive acceleration. Think of this slope as money. If your bank account had negative $80, and then negative $60, and then negative $40, and then $0, what, happy or sad? Yeah, you're happy. That's a positive change, okay? That's positive acceleration. This is also positive acceleration. This is speeding up with positive velocity. This is going to be negative acceleration. I'm slowing down with positive velocity. This would be negative acceleration. Why? Am I speeding up or slowing down here? Look at time. Is it getting steeper or more shallow?
Steeper.
So I'm speeding up. And the velocity, positive or negative? The slope, is it positive or negative?
Negative.
Negative. So if velocity is negative and I'm speeding up, acceleration is negative. Look, any part of the graph that has a smile is positive acceleration. Any part of a graph that has a frown is negative acceleration. If you chance to meet a frown, do not let it stay. Quickly turn it upside down and smile that frown away. Just something to think about. Okay? Now. Oh, it's goofy. Okay, we're going to play a game. With your neighbor, I want you to come up with 4 everyday examples. One for each of these categories. The first category, we're not going to define a coordinate system. The acceleration vector is pointing up, by which I mean towards the ceiling. And the object is speeding up. The second category, the acceleration is still pointing towards the ceiling, slowing down. Third category, the acceleration is pointing down towards the floor, speeding up. Last category, acceleration pointing towards the floor, slowing down. With your neighbor, 4 examples, go. First category, acceleration up, speeding up. Who's got an example? Raise your hand. Yes, sir.
Shooting a rocket.
A rocket, and what's the rocket doing? Blasting off. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Good. Any other example?
A balloon.
A balloon that you've let go and it's, okay, that's so cute. Some kid lost his balloon. Okay. Second case, acceleration up, slowing down. Who's got an example for me? Back in the back.
Riding a bicycle up a hill.
Riding a bicycle up a hill, steep hill, okay. Baseball, which way is the baseball going? Up.
Shooting a rubber band.
Shooting a rubber band, which direction?
Up.
Up. Okay. I just had 3 examples of things going up. And that's why we're doing this game. Folks, there are 2 vectors that describe motion, the velocity and the acceleration. The velocity is also visual if you have any kind of an imagination. As you're going down the road, you can see this great big long red vector going out your front windshield. The faster you're going, the longer it is. Unless you're in reverse, then it's out your back windshield. You can see it almost. The acceleration vector, not so. Acceleration vector, you have to use your gut. If you're speeding up, it's in the same direction as the velocity. If you're slowing down, it's the opposite direction. Now, if the acceleration vector is up and I'm slowing down, I'm looking for cases where the velocity vector is down. Now who's got an example?
Parachute.
A parachute. You just open the parachute, okay, and you're slowing down. How many of you done that? Jumped out of a plane with a parachute? Don't do that ever again. Your mother called. Don't. Okay. Any other examples?
Throwing a balloon down.
Throwing a balloon down before it turns around. Pretty sure you mean a helium balloon.
Yeah.
Yeah, okay. Okay, what about this one? You dive into water. Once you hit the water, you're still going down, but you're slowing down, so your acceleration is up. All of these examples have to be of things that are moving down and slowing down. Now, case 3, something that has acceleration down and is speeding up. If it has acceleration down and is speeding up, its velocity vector must also be down. Can you give me an example of that? Any example whatsoever? Can you?
Tripping and falling.
Tripping and falling. An old guy example. Okay, anything that's falling. Anything that's falling is going to be an example. So, falling rock. Okay. What about this case? Acceleration down, but it's slowing down, so that means the velocity vector must be up. This is where all those examples fit that we talked about before. Shooting the rubber band up, throwing the ball up. Okay, so a ball thrown up. Now, yes?
What about terminal velocity?
Oh, very good question. What about terminal velocity? We can't really discuss terminal velocity without talking about forces, which would be the next part of the class. But in all of our problems that we're going to deal with on the exam and the homework, we're going to use heavy objects like cannonballs and ignore air resistance so that we don't have to deal with terminal velocity until we get to where we actually can understand it with a free-body diagram. Thank you. Now, all 4 of these examples can come from this one demonstration. Okay? Let's look at it. You point at which board I'm doing the motion for before I let go, before I launch it. Okay? Point. Be that up there. As it's going up, before it reaches the top, where would it be? Down there. It's coming back down. Okay? And then I catch it and slow it down. There. And right at the top, the acceleration is what? 0. Oh, really?
Still negative.
Gotcha. Now let's think about that. Acceleration is how much the velocity is going to change in the next little bit of time. If that pen got to the top, it has to stop to turn around. If it had a speedometer, it would read 0 up there. If the acceleration were also 0, what would happen? It'd just hover. That would be spooky. We'd call the Ghostbusters. Okay? Now, if we use our operational definition for acceleration, it was going up, and then a little bit later it's going down. I've got to take those vectors and I've got to put them tail to tail. And then I ask myself, what vector would I have to add to a vector up to get me a vector down? That would be my change vector. So at the top, my acceleration is down. Down. Okay. Fun little exercise. You're standing next to a tunnel entrance, exit, and you see two cars that are side by side as they leave the tunnel. But one of those cars is in the act of passing the other. We're told that the red car has a velocity of 40 meters per second, an acceleration of 20 meters per second per second. The blue car has a velocity of 20 meters per second and an acceleration of 40 meters per second per second. Which car is passing the other one at the instant they are leaving the tunnel? Is the red car passing the blue car, or the blue car passing the red car? Okay? Last call. Okay. The democracy says B, but physics is not a democracy, and the answer is not B. If I look at the operational definition of velocity, it's delta x over delta t, where I've taken my delta r and put it in one dimension, in a horizontal dimension. Now, I think we can agree that whichever car is going fastest is going to go further down the road in the next tenth of a second. And that's what it means to pass someone. When your bumper goes a little bit further down the road in the next tenth of a second, you're passing them. Now, I'm not saying that the red car is going to get to Denver first. Somewhere down the road, not very far, that blue car is going to smoke the red car. But right at the instant they're leaving the tunnel, the red one is in the process of passing the blue one. Okay? Now, we have 2.5 minutes. With those 2.5 minutes, I'm going to help you with your tutorial homework. Just one of the hardest problems. You're asked to consider a ball going up and then down a ramp. You're asked to draw position versus time, velocity versus time, and acceleration versus time graphs for two different coordinate systems. I'm going to do the strange coordinate system. I'll let you do the easy one, the more traditional one. The strange one has the positive x direction down the ramp. All that means is you take your meter stick and you turn it so that the numbers get larger positive down the ramp. Now, if we look at that ball, early in the motion it's near large positive numbers. Then it gets close to 0, and then it goes back to large positive numbers. So maybe my position versus time graph looks like this. Yes? No?
No.
No. Those straight lines indicate uniform motion, and this is not uniform motion. So I would have to have something like this. Now folks, this is the piece that some of you are missing. Once you have that, you have everything. To find the velocity, I just look for the slope of the tangent. Okay? Now that's a very negative slope, so I put a very negative value. A little bit later in the day, it's not so negative. A little bit later in the day, it's 0. A little bit later in the day, it's a little bit positive, and then very positive. That's my velocity versus time graph. Now just like the slope of that is this graph, the slope of that is this graph. Since I've got a straight line with positive slope, I always have the same positive value for acceleration. Now, we have chosen a coordinate system where positive x is down the ramp. If I have a positive acceleration, that means the acceleration is down the ramp, which is what we knew from tutorial. Okay, now you're going to do the other coordinate with the x direction, positive x up the ramp. Have a good weekend, folks.